My name is Brian Kraft, and this is my CSC480 Assignment 1 puzzle solver. I'm just going to quickly walk through the code, which is on my GitHub repo, and the link will be included in the homework. So I have three classes: a node, a tree solver, and then a queue class. And node has a static function that gets the heuristic cost, so you pass it the goal state and the state of the node, and then it just returns the heuristic cost depending on what function you set. And then these are all the parameter or the attributes of a node. So we have a key, a state, the parent, the cost, the depth, the heuristic function we're using. I include the goal state so that when we initialize a node, we can just get the heuristic cost really quickly. The moves it can take, and then the total cost. And then upon initialization, I run the getMoves method, which is hard-coded in just depending on which position the blank is in. There's a certain set of moves that the node can have. And then we have the movePiece method, which takes the node, it takes the state and a move, and then depending on what move you give it, it returns the new state. And it also returns the value of the piece that was moved, because that would be the cost. And so then the queue class, all it does is it has a queue, which is just a list, and then a search algorithm. And then the return node method just pops nodes off the queue, and if needed, it sorts the queue before it pops nodes off, depending on which search algorithm you're using. And then we have a search tree solver class, which you give it a goal state. So that comes from the initial node you pass into the tree. And then it has a root node, which is initialized to the current node, and then we make the root node. And then it has the search algorithm, the heuristic function, which also comes from the node, iterative deepening, which is just a Boolean, and then these keys and the move counter is just used to iteratively create nodes, and then store those nodes in the queue, right? So we have a key for them. And then and then we have a limit, which is just used for iterative deepening, and then the depth counter. So that's performed with iterative deepening. Upon initialization, we run the solver, which basically is going to loop through. It's going to do current state checking right here. If the current state is equal to goal state, that's goal state, I mean. And then it's going to do repeated state checking. So it has a list of visited states. If it's not the goal state and it hasn't been visited, what's going to happen is it's going to go through the possible moves and just iteratively create nodes and add them to the queue. Depending on which search algorithm you're using, it's also going to go through and see if the state of that new node we create is already in the queue, and if it is, it keeps the one with the lowest cost. And then if we're using iterative deepening, what happens is if our depth counter reaches our limit, then we basically reset everything and we add one to the limit so it can continue to go to further depths. If the state has already been traversed, then what happens is we sort the queue and remove the object from the queue, and then we just pop off a new node. Once everything's done, it's going to go through the tree and it's going to print off the actual path to get to the solution. So I'll show you that. In this case, we're just going to do breadth first on easy since it runs really quickly. And you can see it says, alright, this is the initial state, and so we're going to move the 6 down, so here to here, so that's cost of 6. And then we're going to move this 2 to the left, right, so 2 to here, and now the cost goes up to 8. And then it does that until you hit your goal state, and then it has your total cost, number of moves made, the max queue length, the nodes pop, and your runtime. So it puts out the solution. Just to show a little bit of a harder one, we're going to use the Euclidean distance A* search on the hard state, which was the third heuristic function I made. And if you go through, you can see it made it in 38 moves, and it didn't even take a second and a half, which I thought was pretty impressive. I'm going to put all the code on GitHub also and turn it in. If you want more information on it, please feel free to take a look.